Now we talk about the spin quantum number. This is the last quantum number that allows us to describe the specific electron present in an atom. Now, the spin quantum number doesn't actually derive from the Schrodinger equation like the principal quantum number, angular quantum number, or magnetic quantum number do. But its origin is actually kind of interesting. One thing that I kind of bypassed in the last lecture, but I'll mention right now, is that in the emission of the helium atom, regular helium, uncharged, where you have more than one electron, the predicted emissions of light that helium could actually have matches excellently with the observed and experimentally values that we get in the laboratory. And this is via the Schrodinger equations. The Schrodinger equation is fantastic at predicting what happens in multi-electron atoms. But there is one caveat associated with that too. When you have more than one electron, the mathematics becomes so complicated that technically speaking, solving the Schrodinger equation to exactness is actually impossible as of now. There is no known way of solving the Schrodinger equation for multi-electron atoms. So we actually use numerical methods to approximate it as best as we can the answer, and the answer is, a little bit, it has some error associated with it, but for now it actually works out relatively well. Okay, nevertheless, that's a different issue altogether. What I'm trying to get at right here is that when you look at the emission of light of helium, you have the different colors, and yes, we have, using the Schrodinger equation, predicted those particular emission lines pretty accurately. But something interesting happens. If you actually place the excited helium that's emitting light in the presence of a magnetic field, a strong enough magnetic field, what ends up happening is that each one of these emissions of light end up splitting into duets, into basically an energy portion that is slightly higher than the original one that we started with, and another one that's slightly lower than the original one. In essence, basically, you increase by some amount of energy or decrease by some amount of energy from the original value where the original line was appearing. And the idea pretty much is that if you have a magnetic field and all of a sudden you're increasing and decreasing the energy of light coming out of it, then that means that there is some magnetic component associated with the electron jumping from one energy level to another, emitting this light that gets affected by the magnetic field itself. And if you dwell enough into the physics of it all, ultimately what this ends up telling people is that for the electron to actually be affected by a magnetic field, what needs to happen is that the electron itself has to be generating its own magnetic field. And there's one way in which that can happen. The electron already has a charge, and it is known that if a charge moves, it will generate a magnetic field. So the way an electron can actually generate a magnetic field, being the case that it already contains a charge of its own, -1 charge, is for the electron to spin on its own axis. The same way that the Earth can spin on its own axis as well. Now, the presence of this magnetic field and the rotation ultimately creates a magnetic field from the electric charge of the electron. And the thing is this, the rotation of the electron could be counterclockwise or it could be clockwise. And depending on how the rotation happens, the magnetic field could go in the direction upwardly as shown here on the graph on top, or it could be going downwardly as shown in the graph here below. These are really the only two possibilities. As far as spinning on your own axis, you can either spin counterclockwise or clockwise. There's no other possibility. So we assign, since there's basically two possibilities and you can have one or the other, half of the time you're going to be positive spin, half of the time you're going to be negative spin. So pretty much we assign a new quantum number called the spin quantum number, and the value assigned to it is plus or minus 1/2, since you have only two possibilities. Now the electron spin number has one specific consequence. Since the electron can only be rotating clockwise or counterclockwise to give you spin up or spin down quantum number, that means that for any particular orbital that you can have no more than 2 electrons present in it. And this is what we called the Pauli Exclusion Principle. This is also a principle that applies to every other particle known as fermions. Electrons, protons, they're all fermions and they follow this Pauli Exclusion Principle. Alright, so one way to look at it, at least graphically, is to kind of draw the orbitals in a rather peculiar way. Instead of drawing the orbitals out the way we did in the previous videos, where we actually drew the lobes, we filled in the shaded regions, we left the unshaded regions, the way they were, etc., etc. What we do is we draw a box or a line for every orbital that can be present in a set. So the d orbital can have 5 particular different orbitals present, so we draw 5 boxes. The p orbital could have 3 different orbitals present, so we could draw 3 boxes for the p orbitals, 1 box for the s orbital, and 7 boxes for the f orbitals. Alright, now that being said, looking at this whole thing here, we could actually depict the exact set of 4 quantum numbers that each one of these electrons has. And the idea is that no more than 1 electron can have a unique number of quantum numbers. You could have some that are the same, but at the very least, one out of those quantum numbers has to be different. So the idea right here is that if you look at the 3D orbital, automatically we know that the principal quantum number is 3, since that number 3 is present in there, in the symbol. And because the orbital is d, we know that the value of L has to equal 2. Alright, now here's where we're going to look at the individual electrons. And by the way, you may have noticed that I have some electrons basically depicted here by this top arrow or down arrow figure. Each one of those things represents an electron. And the ones that have the top arrow represent the positive half spin of the electron. The ones that have the down arrow as a drawing represent the negative half spin. So we're going to use that for the number denominations. So here I'm going to redraw each one of these orbitals, right? So, or excuse me, each one of these electrons. Starting from left and going all the way to the right. So we have the red one, then the black one, then the blue one, the green one, the pink one, the orange one, and the purple one. Exactly in the same order as if you go from left to right in this drawing. Alright, now, the other thing that you may have noticed is that I also wrote down these numbers here. These numbers are not just random numbers I happen to draw out. They're actually the M-Sebel values associated with each one of the orbitals. And the idea is that because the value of L is 2 as a result of having a d orbital, M-Sebel can go from -2 to +2. And quite literally, that's how you assign the numbers for each one of these boxes. You start with -2 and you go all the way up to +2. Alright, so now each one of these boxes will have a number associated with it, which is in essence the magnetic quantum number. Alright, so looking at the first electron, the red electron, we know that n equals 3 and L equals 2, and that's true for all of these electrons. The difference is going to come in these two other numbers. M-Sebel for the first electron, the red electron, is -2 because it resides in the -2 box. And because it's pointing up, that means that M-Sebel is positive 1/2. Now the next electron, which is also in the same box, will have an M-Sebel value of -2, but because it's pointing downwards, the value of M-Sebel will be -1/2. And it's because of this difference in the M-Sebel numbers that these two electrons are distinguished from one another. Now moving on to the next electron, the blue electron, this electron is on the -1 box, so M-Sebel will equal -1 for that electron, and since it's pointing up, it will have a value of +1/2 for M-Sebel. The electron in the same box, which is pointing downwards, will still be M-Sebel equal to -1, but M-Sebel will have to be -1/2. The electron in the middle box has some M-Sebel value of 0, and because it's pointing up, it's going to equal a value of +1/2. The next electron is on the M-Sebel equal to 1 box, and it's pointing upwards, so it's going to equal 1/2 for the m sub s value. And the last one, which is on the m sub l equal 2 box, which is pointing upwards, will have a value of 2 and 1/2 for the m sub l and m sub s values respectively. And altogether, of course, you gotta remember that each one of these electrons has n equals 3 and l equals 2 also associated with the other two quantum numbers. So this is a graphical way of showing, what kind of electrons you have. And in the entire picture, what you can see is that no two electrons share the same number of n, l, m sub l, and m sub s. At the very least, one of these numbers is going to be different, at the very least. Alright, and also what this means is that you can have at most 2 electrons per orbital and no more than that. Alright, so we're going to stop right here, and in the next video we're going to start looking at electron configurations for atoms, ions, and exceptions.